Uh, Go ahead. Thank you.
Thank you. Um, okay. Um, if you cannot see my screen, please interrupt me. Um, Hello, everyone. I'm Ling Tu. This is a joint work with Xiaomi Ouyang, Professor Jiayu Zhou, Yuze He, and my advisor, Professor Guliang Xing. And today I'm going to introduce FedDL, Dynamic Layer-Wise Federated Learning for Human Activity Recognition. Human activity recognition has lots of applications such as healthcare monitoring and smart home systems. And these systems usually need to recognize a wide range of activities like medicine taking, indoor-outdoor activities, and meal events. These kind of activities normally using ambient sensors and body-worn sensors. So considering most of the sensing data in this scenario are multidimensional, deep learning methods are often needed for accurate human activity monitoring. However, current approach is mostly based on centralized learning that requires the user to send raw data, which impose significant privacy concern. So how about we store the data locally? Federated learning is a new machine learning paradigm. It enables collaborative model training while keeping the data residing on devices. In federated learning, user upload local models instead of data sets to the server, and the server learn cloud models by averaging combining all the local models. However, the single global model is not accurate for all users, as shown by several recent papers. Moreover, transmit the model weights back and forth will cause significant communication overhead. So to deal with these limitations of federated learning, we have two key insights. One insight is that there exhibits intrinsic similarity among users' activity data due to like human biological features, physical environments, or like sensor biases, as shown in the recent papers. And we test one human activity recognition data size and visualize the data distribution of 6 users' data. And from this figure, we can see that there exists a clear grouping relationship among the 6 users' data. And such similarity among users is also reported on other human activity recognition data sets, as shown in recent paper. So based on this kind of observation, we think like we can improve the learned model accuracy by facilitating collaborations among similar users. Another key insight is that the degree of the similarity among users' deep models reduced from the bottom up, as shown in the paper 4 and paper 5, which suggests that we can exploit such similarity of models and aggregate them in an iterative layer-wise manner rather than like aggregating whole models. As shown in this figure, 2 users only share their lower 2 layers as their model upper layers are more user-specific. We now exploit different model sharing schemes and their impact on model accuracy. We tested on data of like 6 users from the Hardbox datasets and visualized the relationship among 6 users' data through a correlation matrix by computing the Pearson correlation coefficients between each pair of users' data. And we can see that there are 2 groups, and the user within each groups are of different degrees of similarity. And this observation inspired a dynamic sharing structure where only the user with a similar data distribution should collaborate in learning, and users who are more closely related to each other will share more layers of their models. So based on this idea, we designed a new scheme like layer-wise sharing. And we implement more sharing structures and compare them with layer-wise sharing. we see that the model based on layer-wise sharing structure gives highest testing accuracy. So motivated by these results, we attempt to generate the layer-wise sharing structure from user relationships to improve the model accuracy. However, the correlation matrix of users' data in the left figure, this figure is like global information that cannot be obtained on a server without accessing the data of users. So we designed a dynamic sharing scheme to learn the similarity of users' model weights and generate the layer-wise model sharing structure accordingly during the federated learning to improve the model accuracy. We named this dynamic layer-wise federated learning system FedDL. FedDL learns the grouping relationship of the local models and then merge only the lower layers of the model in a bottom-up layer-wise manner. And now I'm going to introduce the hierarchical training procedure of the FedDL. First of all, the local model of each user is optionally initialized randomly or from a pre-trained model. Then FedDL going to perform model grouping and model merging in a bottom-up layer-wise manner. So first, it performs the grouping for the first layer, and then merge the first layers of the local models according to the grouping results to get a stable models. And then it computes the grouping results for the second layer and merge the models with the lower two layers sharing according to the grouping results for the lower two layers. And this kind of like iterative model grouping and model merging process gonna repeat to reaching the output layer. So for this case, it's only 3 layers. So like in this picture, I only show like 2 layers process. And each model aggregation involves 4 steps as shown in this figure. First, user perform multiple epochs of local training and then upload local models to the server. And then the server gonna group user based on the model affinity obtained from models testing results on a common sample size using KL divergence. And after that, the server compute the weighted average of local models based on the grouping results, and then generate further personalized model through the weighted average of the local models and their corresponding average models. And finally, the server transmits the personalized model back to the user for local training. And next we're gonna introduce the two components. One is like user grouping, and the other one is model merging. So FedDL learns the underlying relationship of users based on their model affinity. Normally, the element-wise weight distance like L1 or L2 norm have been widely adopted to measure the model affinity. However, they have like a severe limitation in modeling affinity of deep models because the neurons of each layer in hierarchical models are permutable. Besides, it's computational inefficient to measure the norm distance of high dimensional weights for complex hierarchical models. Therefore, instead of like directly analyzing the weight matrix, FedDL tests all local models on a reference distribution in the form of a common sample size, and then measure the model affinity using the KL divergence of the different model outputs. So based on the grouping results, FedDL merged the local models in a layer-wise manner. This figure illustrates the layer-wise model sharing at the server. So first, based on the grouping results of the lower 3 layers, the local models from the user in the same group were gonna be merged by computing the weight average. And the weight average coefficients of each group member indicates how close the member is tied to the group. And also after merging the layers of the models into shared models, the server gonna further personalize the shared models for each user by aligning each local model with its corresponding group model. FedDL take advantage of the dynamic layer-wise sharing scheme to improve the communication performance. Specifically, FedDL reduced the number of the parameters that each user needs to upload to the server. From this figure, we can see that only the lower three layers of the models are necessarily transferred between server and users during the model merging iterations, which will significantly reduce the overall communication overhead during the federated learning process. Besides, FedDL further reduced communication overhead by stopping the upload of each model's user-specific layers whenever possible. And moreover, the model trained using FedDL converge fast, even with a small number of local training runs, which is detailed in the evaluation. So FedDL can use a small number of global training runs to reduce the communication costs without reduce the accuracy. For the experiments, we evaluate the performance using one self-collected data sites, LiDAR data sites, and 4 public real-world data sites for deep learning. We design and implement a FedDL phototype on Amazon Elastic Compute Cloud, and we build a server on the instance and run each user end on one CPU to simulate the federated learning. And the communication between the server and users is implemented locally using sockets. We adopt randomly initialized convolutional neural network for the human activity recognition tasks for all these 5 data sites. And the CNN neural network is composed of 2 convolutional layers, 2 full connect layers, and 1 softmax output layer. And we compare the performance of FedDL with 4 baselines, including federated averaging, federated learning with lower K layers sharing, and federated transfer learning, and also local training approach. First, we validate the design of FedDL on the LiDAR data sites. Specifically, we compare the performance of FedDL with the 4 baselines. And we observe the overall accuracy and also the communication overhead of different approaches on LiDAR data sites. First, we can see that FedDL achieved best accuracy performance with a mean value equal to 0.98, and the interquartile range is also very low. Besides, it's also showed that FedDL saved about 42.6% communication overhead compared with the Fed average and the P-Fed-Me. In Fed average and P-Fed-Me, they both share the entire models during the federated learning. And we further evaluate the performance of FedDL on different data sites, including the UWB data sites, depth images, and 2 IMU data sites. We can take a closer look at the hardbox data sites first. So as showing this figure, the mean accuracy of FedDL outperforms other learning paragons. For example, it outperformed by 25.8% to Fed average and by 12.5% to P-Fed-Me. Besides, for this, the effective of the communication optimization, FedDL is also able to maintain a relatively low communication overhead. So both FedDL and FedPer have a relative low communication cost for all the other data sites, because they only share part of the model layers among users. So similarly, FedDL outperforms other learning paradigms when applied to other data sites. And to verify the scalability, we evaluate the performance with increasing number of nodes. First of all, the accuracy performance, we can see that in our configurations, the mean accuracy of the FedDL outperforms other approaches. Besides, FedDL has a smaller variation of accuracy, which means that it can improve model accuracy for most nodes. And for the communication performance, when the number of involved nodes increases, the communication cost of other methods increases dramatically, while the FedDL maintain a relative low communication overhead, which verify the scalability of FedDL. The number, also the number of the local computation runs is a critical hyperparameter in federated learning. The setting of this hyperparameter shows a trade-off between the computation and the communication. To understand how these attributes affect the convergence of different federated learning methods, we conduct the experiments on depth image datasets with increasing number of local training runs. And this figure visualizes the change of testing accuracy over global runs with different setting of local runs for a specific user. We can see that all the methods have improvements in convergence when involving more local runs. And also FedDL will always converge fast even when the local computation runs is that small. In conclusion, we propose FedDL, a dynamic layer-wise federated learning system for human activity recognition. And it captures the similarity of users' models and generates personalized user models through dynamic layer-wise sharing in an iterative layer-wise manner. And this layer-wise sharing scheme can also improve the communication efficiency. And we also discuss some future work. For example, first, to investigate the trade-off between privacy and the utility for correlated user in federated learning. Second, to extend the FedDL to a wider range of applications where the user's data have a high level of dynamics while exhibiting significant similarities. And for more information, please refer to our paper or visit our website. And thanks for attending our presentation. Any question?
Thank you very much, Lin. Are there any questions? There's one here.
Thank you for a nice talk. Can you please go to slide 11? I'm not sure whether I got that. Have you paired the models?
Right.
So 11. Yes, so you define a validation set and you, correct me if I'm wrong, but you're calculating the KL over the validation set between each two pairs of users, right?
Yeah.
And then you make such clusters.
Yeah.
Okay, and then how this averaging working? So just blindly averaging the models, like linearly interpolating? What is this averaging?
Here we not simply average the local models. We average, it's a weighted average. The key point is how we calculate the coefficients. The coefficients here is when we when we grouping, for example, for the first layer, it looks like all the users belong to one group. But the things for each user, their coefficients is different. Their coefficients reflects how close this each node's bonded to this group. And if it's bonded closer to this group, that means this node's local model gonna contribute more to the average model, to the group model. But if this node's bonded less to the group, it's gonna contribute less to this group models.
Okay, and this averaging means averaging the weights, right? So you
N1
and N2. Okay, but correct me if I'm wrong, but if you blindly average them, we know that N1 and N2 are residing in one basin. Do you know that they can average? Because if you blindly average them, then there would be a barrier. So if one is 99%, the other one is 99, and you've averaged them, that you wouldn't get better than random chance. My question is that how this averaging is working. These are two separated models, right? On on one data set. So if you average them, it's not working.
So like different users model is on different data sites, first of all.
And this is
And,
not pre-trained, or is it pre-trained?
It's not pre-trained. It's like randomly initialized. It can be pre-trained. It doesn't matter. It's like a pre-trained or pre-trained or like randomly initialized. Because like first of all, before you merge them, before you upload to the server, your local models already been locally trained based on your local data. So they are different. They reflect each user's data distribution.
Okay, thanks. Maybe we can continue offline. Thank you.
Okay, thank you.
There's one question in the Slack channel.
In Slack, Junlu asks if this approach also applies to recurrent neural networks.
Yeah, it works for any deep, like hierarchical models, like deep models.
Okay, thank you. So if there are no more questions, let's thank Lin. Thank you.
Thank you.
Very much. And we can move on to the third paper of the session, which will be presented by Xiao Zheng, I believe. The paper is entitled Mercury Efficient On-Device Distributed DNN Training via Stochastic Importance Sampling. Can you put... Okay. Xiao Zheng is a PhD from Michigan State University. His major is electrical engineering. His research focuses on efficient on-device machine learning, federated learning, and AIoT. So, Xiao Zheng, please go ahead.
Thank you, Chair, for introduction. Can everyone hear me?
Yes, please go ahead.
Yeah. Okay. Hello, everyone. My name is Xiao Zheng. The title of my presentation is Mercury Efficient On-Device Distributed DNN Training via Stochastic Importance Sampling. Today, there are many smart edge devices such as smartphones, AR/VR headsets, smart speakers, robots, drones, as well as the massive amount of data they generate on a daily basis. As AI chipsets emerge, the majority of edge devices will be equipped with machine intelligence powered by deep learning to not only perform on-device inferences, but also collaboratively train a deep learning model from the on-device data collected by themselves. Edge devices are connected by wireless network. Therefore, unlike data center setting, on-device distributed training only has limited bandwidth, which leads to longer training time. Existing solutions are focused on improving the training efficiency for centralized clusters. However, it falls short when shifting to edge or mobile environments. Existing solutions are the first approach is the gradient compression. By compressing the gradient, you can reduce the amount of data to be transferred and then reducing the communication time. However, these methods only work after the training is close to convergence or may lose accuracy if compression rate is too large. The second approach is called local SGD, where the clients perform multiple local updates before sending the gradients for aggregations. However, it may deviate from the global optimal model when multiple local steps are performed. The final approach is called overlapping. The idea is to overlap the communication with gradient computation. But it does not work well under mobile environment because communication time is significantly larger than the gradient computation time. So different from previous approaches, Mercury aims at improving the training efficiency to reduce the number of iterations for convergence. The total training time is approximately equal to the number of iterations times per iteration time, which is the sum of computation time and communication time. The idea of Mercury is to focus on training important samples, and by doing so, we can reduce the number of iterations required to conversion. More importantly,